Of week 3 conservation laws and this is part 3. Let's get going. We have so far encountered the notion of conservation of mass, the notion of momentum or linear momentum, and the conservation of linear momentum. We will now discuss a new concept known as energy. And to introduce the necessity or the importance of this concept of energy, let's consider the following example, following scenario. Let's say that you have two billiard balls, each with a velocity of, two billiard balls, one with velocity of 1 meter per second and one with velocity of -1 meter per second, and they are colliding with one another. Let's pretend then that after the collision, one would have 5 meters per second and the other one would have -5 meters per second. Right? Does that sound reasonable? Well, let's think about this for a moment. So the two balls are billiard balls, so they have presumably the same mass. So the total momentum before the collision would be mv of the first ball plus mv of the second ball, same mass. And so same mass, v of the first plus v of the second, that means 1 minus 0 is 0. So, 1 minus 1 is 0. So the total momentum before the collision would be 0. 1 minus 1 is 0. So no momentum before the collision. It would mean that after the collision there should also be 0 momentum. Well, we're told that one ball goes at 5 meters per second, whereas the other goes at -5. So the total momentum after the collision is still 0. So this does not violate the notion or the law of conservation of momentum. But it's kind of weird, right? Because you have two balls that are moving at 1 meter per second each, and then they collide. And after the collision, now they go faster. Have you ever experienced something like this? Probably not. If you did, you might have seen something where something happened in the course of the collision that releases a kick that is imparted onto the two objects. What that means in practice is that momentum is conserved, but something is missing in our understanding or at least in our description of what's going on. And the missing piece has to do with kinetic energy, or more broadly, energy. So we need to introduce a new concept, that of energy. And we will see that energy is a very, very broad concept indeed. And what we will start with is the notion of kinetic energy, defined here in the middle of the slide. So there's more than just momentum conservation in mechanics or the description of the motion of objects. There's also the notion of energy, and particularly kinetic energy. And as it happens, energy is conserved. The energy is something very subtle and complex at the same time, and yet it has a simple manifestation. So through example, we will discuss what it is and how it can be understood. So kinetic energy is a quantity that here in this lecture and elsewhere in the this course we will denote by the letters Ke, standing for kinetic energy. In some textbooks, some other places, you might find that it's just described as K or T or some other letters. Here we will say Ke for kinetic energy. And it is defined as 1/2 the product of m by the square of the speed of an object. So the kinetic energy of an object is 1/2 its mass times the square of its speed. The units of energy are the joule. Energy is such a central concept, is such a critical concept in physics, as well as in other branches of science like chemistry, that it has been given its own unit, and it's called the joule. Joule is named this unit. The joule is named after a physicist who studied the conservation of energy. 1 joule, 1 J, is equal to 1 kilogram times square meter divided by square second. Let me give you an example. Let's start with a car at a mass of 1 kilogram and speed of 10 meters per second. And let's pretend that this car is hitting a standing car with an identical mass. So the two cars have a mass of 1,000 kilogram. The incoming car travels at 10 meters per second. The second car is at rest, v equals 0, before the collision. As a result of the collision, that is just right after the collision, the first car stops and the second car starts moving. And we can then ask ourselves, what is the speed of the second car? And we can also ask ourselves, what happens to the kinetic energy before and after the collision? Well, let's first review what we know having to do with momentum conservation. The initial momentum before the collision is mv. And that comes from the moving car, and only the moving car. 1,000 kilogram times 10 meters per second, that is 10,000 kilogram meter per second. After the collision, the momentum will need to be the same by the virtue of the law of conservation of linear momentum. And so that means that after the collision, the momentum will also be 10,000 kilogram meter per second. However, we don't know the velocity of the second car. We are told that the first car stops, v equals 0, and the second car then has some velocity. Well, given that the two cars have the same mass, P final over the mass of the second car is going to be 10,000 kilogram meter per second over 1,000 kilogram. That's just 10 meter per second. So what we find is that one car came in at 10 meter per second onto a car at rest. The incoming car stopped, and the other car then recoiled, so to speak, at a speed of 10 meters per second. So that's what we learned from momentum conservation. What can we learn from energy conservation, or specifically, what is happening to the kinetic energy? Well, it's quite clear that if the velocity of the car after is the same as the car before of the first car before, it's quite clear that the kinetic energy is also going to be unchanged in the collision. So before the collision, only the first car carries kinetic energy, and after the collision, only the second car carries kinetic energy, and they have both the same mass, both the same velocity. So we have that the kinetic energy is 1/2 mv squared, so that's 1,000 divided by 2, that's 500, times the square of 10 meter per second, so that's 500 times 100, and that's 50,000. Apologies for this. Let's fix this. There we go. So what we find is that the car coming in had a kinetic energy of 50,000 joules, right? That's 1/2 of 1,000 times the square of a 10, right? So 1/2 of 1,000 is 500 times the square of 10, which is 100. So we're talking of 50,000 joules. And we find that before and after, this is going to be the kinetic energy. So the cars cannot indeed have more kinetic energy after the collision than before, unless somehow something happened during the collision that would provide a new source of energy. We'll come to that. Let's consider another example. Let's consider now a truck, a 10,000 kilogram truck traveling at 12 meters per second, hitting a 2,000 kilogram car that is at rest. When the truck smashes into the car will be pushed ahead and will start moving. And this truck is seen moving at 9 meters per second after the collision, so we can ask, how fast is the car moving? Okay. And we already saw this example. So after the collision, we found that the car is moving at 15 meters per second. And so now we can ask, what is the kinetic energy before and what is the kinetic energy after? So before the collision, the kinetic energy is carried by the truck. 1/2 the mass of the truck times the square of the velocity of the truck happens to be 720,000 joules. And after the collision, the kinetic energy is carried by, in part, the car and in part the truck. The truck now goes at 9 meters per second, while the car goes at 15 meters per second. So you will have 1/2 mv squared for the truck and 1/2 mv squared for the car. You bring these two together with the numbers that we just found, you get that the kinetic energy after the collision is now 630,000 joules. Now wait, the two values are different. There's less kinetic energy after. What's going on? We saw that after the collision, the car must have 15 meters per second velocity or speed. And with such a speed, it conserves linear momentum. Now we find that with such a speed, the kinetic energy of the two vehicles together after the collision, or the final kinetic energy, is less than the initial kinetic energy of the truck. So some energy now has disappeared, seemingly. Where did it go? Well, can you make a guess? What happens when you have a collision? You smash your truck into the car, you bend the metal of the car. Bending metal takes force. Bending metal by some distance means doing work on the metal, doing work on the body of the car, or the chassis of the car, or on everything. And this squeezes the car, perhaps even a little bit the truck, and so it modifies the truck, it modifies the car, and the cost of this modification, the cost of bending metal, is where the missing energy has gone. So some kinetic energy is remaining after the collision, but some large amount has been now converted or consumed into squeezing the vehicle against one another, deforming them, breaking them. And so kinetic energy has been transformed into changing the shape of the car. So kinetic energy is not always conserved, as we just saw in this example, but we can state that energy is always conserved. The concept of energy is broader than just kinetic energy, and we will expand on this in a moment. And energy is always conserved. It's not always easy to figure out where the energy is going or where it came from, but energy is always conserved. It's a fundamental law of nature. And this fundamental law of nature is just as important as the law of momentum conservation. It's, however, a little bit tricky. It's a little more tricky because energy can change form. Energy cannot be created or destroyed, but it can be converted from one form into another. So the total energy of an isolated system is constant or invariant. I remind you that isolated system means that a system such that no matter goes in or out of the system, and no influx of energy is given to the system, or the system doesn't output energy into its environment. So total energy of a system being constant means that it doesn't change energy. And it's, as I said, a fundamental law of nature. It's conceivably one of the most important laws of nature. However, tracking and finding the converted energy can be tricky. And in fact, the unit joule that we mentioned is named after the physicist Joule, who figured that such a conversion of energy from one form to another is always present. And he demonstrated that quantitatively and numerically. And so he's the one who showed for the first time, already quite some time ago, he showed that energy is in fact conserved, although it may change form. And the way he did that was he was in the Alps, and he was studying the fall of water, waterfalls, the speed of the water as it fell, as well as the change in temperature of the water as it went from the top of the falls to the ground, and he studied how this could account for a change in the form of energy. More on that later. And so consider now the introduction of a new concept, that of potential energy and the notion of work. And this will then tie in with the notion of kinetic energy and momentum. So let's consider the dropping of a ball of a certain mass m from a height h. We know that, at least if we can neglect air, the presence of air, we know that the ball will accelerate and go from essentially zero velocity to increasing velocity until it reaches the ground. And we know that this ball will be accelerating due to the gravitational acceleration, which is g, 9.8 meters per second. So after a certain time t, the ball will have a velocity v, which is g times t. G is the acceleration due to gravity, t is the time of fall. So we can ask ourselves, what is the kinetic energy as the ball hits the ground? The kinetic energy is 1/2 mv squared, and I just told you that v would be gt. So the kinetic energy is 1/2 m g squared t squared, which is what I obtained by substituting the value gt into the expression for v squared, right? So now I have Ke kinetic energy on the left, 1/2 mg squared t squared on the right. What can I do with this? What can I learn from this? Well, I know that, sorry, to go being back and forth, I know that there's a relation between V and G and T, and there's a relation then between Ke and the time of fall. So I can write that the height of fall is 1/2 gt squared, something we have seen before. And so now I can use this expression to rewrite the expression of the kinetic energy. So kinetic energy we saw is 1/2 mv squared. On the previous slide, we showed that when dropping this ball, it will be equal to 1/2 mg squared t squared. And now we know that t squared is going to be 2h over g. So I can then substitute the value of t squared here by twice h over g, and the 1/2 will cancel the 2, and I will be left with mgh. So the kinetic energy of a ball falling from a height h is equal to mgh. What is this mgh? It's obviously a quantity that depends on the height of the fall, a quantity that depends on the mass of the object falling, as well as g, the gravitational acceleration. The gravitational acceleration depends on the force pulling on the object, pulling it down. Right? And so the force on the object is mg, mass of times acceleration of the object, and this force is acting through a height h. And so this gravitational force then is effectively doing work on the ball. It's applying a force mg, and it's applying this force during a certain path length or distance h. And so we say that mgh is the potential energy of the object at height h. Right? So we will call mgh the potential energy, or more specifically the gravitational potential energy of the object at that height. And so I will stop here, and we will continue in part 4.